The induction system takes air from a forward-facing inlet, which gives the benefit of a slight positive boost from the aircraft's forward speed, and passes it to the carburetor and thus to the inlet manifold. An air filter prevents debris getting through to the carburetor and the engine. The problems of engine icing, particularly engines fitted with carburetors, have been known for some years, but still accidents occur in which induction system icing has been the cause, despite modern fuel metering devices. Atmospheric conditions, particularly of high humidity, a relative humidity greater than 50%, and temperatures ranging from -7 degrees Celsius, that's 20 degrees Fahrenheit, to as high as +33 degrees Celsius, 90 degrees Fahrenheit, may cause icing in the induction system of all types of piston engines. This temperature range and humidity occur throughout the year in the areas of the United Kingdom and Europe, and therefore pilots should be constantly aware of the possibilities of icing and take the corrective action necessary before such problems arise and the situation becomes irretrievable. Basically, there are three forms of icing which affect the induction systems of piston engines which are fitted with carburetors. They are impact ice, refrigeration ice, and fuel icing. Impact ice forms on bends in the induction system and also on the intake air filter. Refrigeration ice, or carburetor icing, forms in float-type carburetors as a result of the low temperatures caused by both fuel vaporization and low pressure acting on the moisture in the atmosphere. Fuel icing is caused by moisture in the fuel coming out of suspension and being frozen by the low temperatures in the carburetor. This ice tends to stick to the inlet manifold around its corners, and this reduces the flow of the mixture into the engine. Once an engine stops due to induction icing, it's most unlikely that it may be restarted in time to prevent an accident, and therefore recognition and correction of the problem is vital. The indications of induction system icing to the pilot of an aircraft fitted with a carburetor and a fixed-pitch propeller would be a gradual drop in RPM, which may be accompanied by engine rough running and vibration. If the aircraft is fitted with a constant speed propeller, induction system icing would be indicated by a drop in manifold pressure or a reduction of airspeed in level flight. When icing is suspected, the carburetor heat control should be selected to fully hot and left in the hot position for a sufficient length of time to clear the ice. This could take up to 1 minute, or even longer, depending on the severity of the situation. Full carburetor heat must always be used unless the aircraft is equipped with a carburetor air temperature gauge. The carburetor heat control provides heated air from around the exhaust pipe into the induction system, which will melt the ice, which then passes through the engine as water. Engine roughness and further power loss may occur as the water passes into the cylinders, and pilots should not be tempted to return the heat control to off or cold, thinking that the situation has become worse since applying heat. Icing is also more likely during long periods of flight at reduced power, such as during a glide descent or letdown for approach and landing. Because the heat is derived from the engine, during long descents the engine temperatures will gradually cool, thus reducing the effectiveness of the hot air system. Where icing conditions exist, select full hot air before reducing power so that benefit is gained from the hot engine before its temperature starts to reduce. To help maintain engine temperatures and provide a sufficiently great heat source to melt any ice, it's necessary to increase power periodically to a cruising setting at intervals of between 500 and 1000 feet during the descent. Additionally, this action prevents lead fouling of the spark plugs. Carburetor icing can occur during taxiing at small throttle settings, or when the engine is at idle RPM. In these circumstances, ensure that hot air is used before takeoff to clear any ice, but remember to select cold air before opening the throttle to full power, and check that the correct takeoff RPM or manifold pressure is obtained. Under no circumstances should carburetor heat be used during takeoff. When using carburetor heat, there are a number of factors which should be understood. The application of hot air reduces the power output by approximately 15%, and also creates a richer mixture which may cause rough running. The continuous use of carburetor heat should be avoided due to the change of mixture and increase of engine temperatures. Heat should be used only for a sufficient period of time to restore engine power to its original level. This will be noted by an increase of RPM or manifold pressure above the original setting when the control is returned to cold. Don't use the carburetor heat once you're clear of icing conditions, but do check periodically that ice has not reformed. The following point should be understood when using the carburetor heat control. Use of the heat control on the ground should be kept to a minimum, as the air is not filtered and may feed dust and dirt into the system, causing additional wear on pistons and cylinders. A functional check of the heater control should be made before takeoff. Engine rotational speed should drop by approximately 100 RPM when heat is applied, and return to the selected setting when turned back to off or cold. If icing is evident on the ground before takeoff, use heat to clear the ice, but return the control to off before applying takeoff power. Check that normal takeoff power is available. When climbing to a new altitude en route, ensure that carburetor heat is selected off. Be aware of conditions likely to cause carburetor icing: damp, cloudy, foggy or hazy days, or when flying close to cloud or in rain or drizzle. Look out for an unaccountable loss of RPM or manifold pressure. Make frequent checks for icing by applying heat for a period of between 15 to 30 seconds, noting first the selected RPM, then the drop of RPM as heat is applied. Listen to the engine noise and check the outside air temperature. Should RPM increase while heat is applied, or the RPM return to a higher figure than original when reselected to cold, then ice is present. Continue to use carburetor heat while flight in icing conditions continues. During glide descents or long periods of flight at reduced power, say below 1800 RPM, apply carburetor heat, remembering to warm the engine for short periods, say every 500 to 1000 feet. During approach and landing, the carburetor heat selector should remain at cold, except for a glide approach. But if icing conditions are known to exist or even suspected, full heat should be applied. Remember, though, that the carburetor heat selector must be returned to cold before applying power for either a roller landing or an overshoot. Engines fitted with fuel injection do not have the problems of ice forming at the venturi, but other parts of the system may accumulate ice with a similar loss of power. Fuel icing may gather at the bends in the system. Impact icing may form at the impact sensing tubes or on the intake air filters, particularly when flying in cloud at low temperatures. The alternate air system fitted to these engines should then be selected and the icing drill followed according to the aircraft checklist. In the low-pressure, continuous flow fuel injection system, which is used on many aircraft piston engines, fuel is sprayed continuously into the induction pipe as close to the inlet valve as possible. The advantages claimed for the method are low operating pressure, good fuel distribution, freedom from icing problems, and the ability to use a pump which does not have to be timed to the operating cycle. In this system, the fuel metering valve varies the pressure of fuel according to engine speed. Mixture strength is varied by a manually operated mixture control valve which adjusts the fuel pressure for altitude or operating conditions as necessary. Because of the method of operation of the injector, no special idling arrangements are required, and a separate priming system for engine starting is unnecessary. The main components in the system are a fuel pump, a fuel control unit, and of course the discharge nozzles themselves, one for each cylinder. In addition, a fuel pressure gauge is fitted to enable any mixture adjustments to be checked accurately. The fuel pumps supply more fuel than is required by the engine, and a recirculation path is provided. Two pumps are provided, arranged in parallel, so that when the mechanical pump is not operating, fuel under positive pressure from the electrical pump can bypass the mechanical pump, so allowing the electrical pump to be used for engine priming, starting, and for emergency situations. A fuel discharge nozzle is located in each cylinder head, with its outlet directed into the inlet port. Nozzles are fitted to individual engines as a set, each nozzle in a set being calibrated for that set only. The fuel control unit is mounted on the intake manifold. It contains three control elements: the throttle valve, the metering fuel valve, and the mixture control valve. The air throttle assembly contains the air throttle valve, which is connected to the pilot's throttle lever and controls airflow into the engine. Notice that the intake manifold has no venturi or other restrictions to airflow. The throttle valve is connected to the pilot's throttle lever and controls airflow to the engine. The fuel metering valve is connected to the air throttle and controls fuel flow to the fuel manifold valve according to the position of the air throttle. Thus fuel flow is proportional to airflow and provides the correct air-fuel ratio. The mixture control valve is connected to the pilot's mixture control lever and bleeds off fuel pressure applied to the throttle metering valve. Thus the air-fuel ratio can be varied from the basic setting of the throttle metering valve as required by operating conditions.